using what we just learned, I can look at this matrix here, and I can see that it is not invertible. So this is saying without calculation, find an eigenvalue. Oh, I know, because I'll just say since A is not invertible, lambda equals 0 is an eigenvalue. Okay, then I'm being asked to find two linearly independent eigenvectors. Okay, so if I'm setting AX equals 0, I'm taking matrix A and I'm augmenting it with zeros, right? And I know because row operations, I would get this, right? So this would mean x1 plus x2 plus x3 is 0. So I'd get this. So my vector x would be this. Looks kind of familiar. x2, negative 1, 1, 0. Whoops, negative 1 I meant. And then x3, negative 1, 0, 1. So two eigenvectors. One of them would be negative 1, 1, 0, and the other would be negative 1, 0, 1. So those are two linearly independent eigenvectors. All right, let's play with some algebra now. Okay, so if x is an eigenvector of A, so what that means is I have this relationship going for some lambda, right? So the dance is going on, x, a, and lambda. So I've got this ax equal lambda x. So now I'm being asked, what is a squared x? Well, let's take this and multiply on the left both sides by a. So this gives me a squared. This here, I'm going to take the time. This is just a number, so I can switch the order of the number and the matrix, right? I could pull the number lambda outside, so I get this. What do I know that ax is equal to? I know that ax is equal to lambda x. So this gives me lambda x. So I get a squared x is equal to lambda squared x. Okay, so I want you to be careful that you're taking the time to write this step, and this step. You can't just go plowing through, because you need to show that you understand lambda is a number and that you get ax is equal to lambda x. All the steps are necessary. All right, so now I have lambda, an eigenvalue of an invertible matrix A. Okay, so that means ax is equal to lambda x. So if A is invertible, that means that lambda does not equal 0, right? All right, so show that lambda inverse is an eigenvalue of A inverse. Okay, so it's always starting with a true fact. This is a very good fact to start with. How about if I multiply both sides by A inverse this time? A inverse. So A inverse times A gives me x. And again, I'm going to take the time to switch these two, because lambda is just a number. And I want to find out what the eigenvalue excuse me, of A inverse is. So I kind of want to say, I want to have in the end A inverse x equals, right? So here's A inverse x right here. So let's multiply both sides by 1 over lambda. Isn't this the same as saying lambda to the negative 1 times x is equal to A inverse x? So I've shown that lambda to the negative 1 is the eigenvalue for A inverse. Oh dear, this example I have to come back to in a second, because that's going to have to do with a theorem on the next page. All right. So show that A squared is the 0 matrix. If A squared is the 0 matrix, then the only eigenvalue of A is 0. Okay, so let's start off with something we know. like that. Then let's multiply both sides by a. All right, so this gives me a squared, and I'm going to move that lambda in the front there. Okay, so they're telling me a squared is 0. So this side turns into 0, right? So I have lambda times, and then what do I know about ax? That's equal to lambda x. Okay, so I have 0 is equal to lambda squared x. All right, so how do I know that the lambda, so I'm trying to find out to show that the lambda is equal to 0. I have two things multiplied together to be 0. So what do I know about x? Remember, x is a non-zero vector. That was one of the things in the beginning, right? So if x is non-zero, that must mean that lambda squared is 0, which means lambda is 0. So that is the only eigenvalue.